Okay, so for homework 2 of computational methods, the first part is very simple. We would like to numerically demonstrate the central limit theorem. Okay, and this all revolves around the basic definition of the central limit theorem, and it's in the context of inferential statistics. All right, and that inferential statistics essentially means that you do not know what the population parameters are, but you can approximate them, estimate them based on the sample. And the central limit theorem goes as such. So let's say we have a data set with rows, or rather columns first, columns equal to 50, okay? And rows will have some fantastically large number, like 1 e to the 6, and we would like to cast that to an integer, okay? And for the central limit theorem, you notice we have a very large number here. The central limit theorem states that for a very large sample size, so 50 trials for a very large sample size, if you take the average of each trial, each mean, and then you plot them out, that will resemble a Gaussian distribution. It is the most likely distribution, right? So let's go off and demonstrate that. So let's say, oh, we need to let's call this samples maybe. We need to go off and do np.random.uniform from, let's say, from -1 to 1. Okay, so all this means is it's going to create a uniform distribution. Okay, we're not going to see a Gaussian distribution. Each point will be uniformly distributed. Okay, and let's make sure those are floats. And I believe the next parameter is size. Size is equal. Let's say I believe columns goes first. N columns to n rows. Okay. And let's take a look at that. It looks something like this. So we have a whole bunch of random numbers that are uniformly distributed. Theoretically, if we plot this out, it looks just like a rectangle, right? Let's say, and then we would like to go off and take the average, okay? Row, average. So the rows, take the average of each row. This is a fantastically large trial size, okay? So np dot average samples axis equals 1. So the row, okay? And we'll put that into a histogram, np dot, so let's do, I believe bins, then count, right? Bins and count is equal to np.histogram. We're going to use the histogram function to split it up into a select number of bins automatically, okay? And we're going to put row average in it, and we would like 50 bins, something like that, right? So let's just double check, is bins correct? Yes, right? I think so. Let's try and plot it out and make sure it's all a-okay. So fig equals make subplots and fig.add. Now we'd like a bar graph this time, okay? And x is equal to the bins and y is equal to the count, okay? It's that simple. And hopefully this is totally wrong. I think I flip-flopped this here. Maybe it's bins, count, and then bins. Not quite right. What's wrong? I think I flip-flopped the size here. It should be rows then columns, maybe? N rows, columns. There you go. So this is super simple numerical demonstration. It's saying that if for a uniform distribution, or in reality any distribution, for a fantastically large number of trials, if you take the average of each trial, okay, and then plot it out, that distribution will end up resembling a Gaussian distribution, and this is how inferential statistics work. You may not know what the parameters of the population are, but if your sample size is large enough, you can make a pretty good guess and estimate to a certain level of confidence what the population parameters are, okay? So this is the first way we're going to demonstrate the central limit theorem, and after this, we're going to go off and demonstrate another way and show that the Gaussian distribution is actually the most likely distribution, okay? And that's going to get very interesting. So we'll see you in the next video after this. Okay, so now we're on the iPad. Let's go off and show the Gaussian distribution in a different way, okay? And let's set this problem up here. So let's say we have a class where you can score from 0 to 10. In other words, you have 11 possible scores. And let's say this class has 50 students. Okay? In other words, this class can be arranged as such. Student A may have a score of 10, B 10, C 10, so on and so forth, right? D 9, and E 9, so on and so forth. The question is, if we split it up into these bins, 11 bins, okay? So 11 bins. We know that the number of permutations for the entire student base is 50 factorial, and you know that from your basic statistics class. The question is, with these bins that we have, this has an arrangement of 3. For this particular example, 3 factorial. The question is, how can we distribute these scores between these students so that there is the maximum number of permutations? And this is the idea of maximum entropy. Okay, and it looks something like this. It's going to look like n factorial. So let's call 50, this is n, the number of students, and n sub I, I'm going to keep referring to this. N sub I will refer to the number of students within a particular grade, or in other words, a particular bin. Okay, so this is the entropy equation. This is the number of permutations possible for this distribution of students and scores, and it's going to look like this. Big pi is going to be it's like a summation, except the operator in between elements is, instead of addition, the operator will be multiplication. Okay, it's very simple here. Pi ni factorial. This is going to be our entropy, or our number of permutations. We want to maximize this entropy. In other words, finding what is the distribution that will allow us the maximum number of permutations, and therefore is the most likely distribution. So the idea here seems pretty straightforward, right? This looks like a maximization problem, a root solver problem, where we can go into SciPy and use the root solver package to maximize this expression. Okay, and by the way, this is the parameter that we are allowed to adjust, the n sub I, in other words, the number of students in each particular bin or each particular grade. So we have 11 parameters to adjust. Okay, and it might seem pretty simple, but it seems like we can just go off and plug it in to a root solver and find out what's the most probable distribution. And while that may work in some cases, it has one fatal flaw. That flaw being, it's not at all impossible to have something like 1,000 students in a particular cohort or a particular school, right? Or even 500 is a bit overkill. The problem is that factorial, 1,000 factorial, is impossible to calculate by brute force for a computer, right? I could go demonstrate on Python, but in the collaboratory environment, the maximum seems to be 100 factorial, and after that, greater than 100 factorial, it starts overflowing. It thinks that it's an infinite number. Okay, so that's the big problem. The big way to get around that is something called Stirling's approximation. Okay, so Stirling approximation. And that will be the crux of how we're going to manipulate this equation so that it can work for very large numbers in a root solver. And Stirling's approximation is very simple. It states that the natural log of n factorial is equal to natural log of n factorial minus n. I believe it's something like that. Let me double check here. So Stirling's approximation. Hopefully my memory is not failing me. That's right. Oh, n natural log n minus n. And you see this value at the end. That's just error. And we're not going to worry about here because for Stirling's approximation, the greater n is, the more accurate the approximation. So that works for our purposes. Let's go off and do this. Okay. Let's say, so you know that a factorial is 5 times 4 times 3, so on and so forth, right? You know what a factorial is. In other words, a factorial is going to look like natural log of n1 times n2, so on and so forth. So you know from your log rules, that inside the logarithm, if you multiply, that will turn into addition outside the logarithm. So this will become natural summation. Let's say n equals 1 to 2i. Okay, of what? Of natural log of I. Okay. Same thing. That's the only manipulation we've done. Another thing is that in the past, you've most likely done a lot of approximating integrals as summation, right? Like Riemann sum or otherwise. In this case, it is convenient for us to instead approximate this summation as a integral, because if you plot out a logarithm, right, and right now it's discretized, right? So we're adding a whole bunch of point values of integers. For the greater the number is, the more we can approximate it as, well, that's just area under the curve, right? So let's go off and do that. We're going to approximate this summation as a how do you say, integral from 1 to I of natural log of x dx. So if you go off and let's do n actually, call that n. If you go off and evaluate that, what does that become? That becomes n natural log of n minus n. There you go. Check that out. There is Stirling's approximation. Okay, so now that we've gotten Stirling's approximation out of the way, I've gotten ahead and taken the liberty to move us to a new page for some more room and copied over our entropy equation. Okay, because this is an optimization problem, this allows us a certain number of degrees of freedom. Okay, and the first of which I've demonstrated as such. Because it's an optimization problem, we have one parameter to adjust. Okay, in other words, if we put a function on the outside, so long as we're not adding more independent variables to adjust, then it will not matter from the point of view of the solver, right? All the solver is trying to find is what values of that will make the function the largest possible value. Okay, so in this case, I've taken the natural log of the whole function, okay? And that makes no difference from the perspective of the root solver. Or not root solver, minimization solver is what we'll be using. Okay? And because I've taken a log, I can now use logarithm rules to split this apart. This becomes natural log of big N minus natural log of little n. Okay? And because there's a multiplication series on the inside of the natural log, as you know, the multiplication inside of a natural log becomes addition outside of the natural log. So it looks like so. Another thing is that, another useful thing about optimization problems is that for any parameters, I should not say parameters, for any elements which do not have the independent variable, it is completely constant. That does not, the solver does not care about that at all. So we can completely ignore any constant values. In other words, the natural log of big N factorial, that never changes, and the parameter of adjustment is not inside of that function. So we can just ignore it. Okay? Oh, don't forget the factorial here. So here is where we can go off and apply Theorem's approximation. We say that it's going to equal the negative summation of this. Right? And we can use some summation rules here, and you know that the summation, you can split apart summation. So negative summation looks something like this, plus summation ni, okay? And the reason I do that is to point something out. The summation of number of students in each grade is just going to equal n, which doesn't matter. So this doesn't matter to the optimization problem. So we are left with negative natural log of ni. Okay? Okay. So we can go off and further manipulate this problem as such. We can define the probability of getting a particular grade is equal to the number of students who got that score over the total number of students. In other words, ni equals p sub I times n. And we can substitute as such. P sub I times n, natural log of ni, natural log of p sub I times n. Okay? As you know from the summation rules, constants may go on the outside of the summation. So n summation of p sub I. Okay, and we can split this logarithm apart with, what do you call it? Logarithm rules. Okay. And we go off and distribute now. Okay, the summation is still there. Negative is still there. Okay, p sub I, natural log of p sub I, plus, well, let's go off and do minus here. Minus summation, that's a horrible summation, summation of p sub I times natural log of n. Okay? Okay, so here, I believe, is where I need to be a little careful and designate which one doesn't matter. Okay? I would say that because this natural log of n is constant, I believe that I need to be super careful here. One of these cancels, and I'm rather sure it's this. And I believe that the reasoning behind that is that, oh, by the way, I neglected to put an n out there. The summation of probabilities, right? The summation of probabilities is very simply equal to 1. Okay, so the summation of probabilities is equal to 1 multiplied by a constant, so therefore the root solver doesn't care about this at all. As opposed to this left expression, this has a probability p sub I expression inside of the natural log. So that will cause it not equal to 1 when it sums up. Okay, so this is the one that matters. Okay, and there you have it. This is going to be the expression that we're going to maximize in our root solving in Python. Okay, so we'll meet back up in Python and we'll continue solving out this problem. All right. Okay, so now we've gotten done deriving this entropy equation. Let's go off and try to maximize it to find out what the most probable distribution is in Python. So if you recall, we'll call this neg entropy. That is because we're using the minimization function, so not quite maximizing, but if we maximize the negative of our equation of interest, then in effect, we are maximizing it. So negative entropy, it takes in P. P is the probability of, am I recording? I am, good. P is the probability that a student will achieve a particular grade. So for this current example, it's from 0 to 10. In other words, P is a array of values that for the probability of a student falling in each bin. Okay, and we'll see that in a second. So the expression that we had derived was pretty simple. It's the sum of P multiplied by the natural logarithm of this probability, right? So maybe we'd like to go off and minimize that. So minimize neg entropy, and we need a guess. So what is that guess? Well, let's do something arbitrary like np.zeros n being the number of grades there possibly can be, so 11, 0 to 10, and well, let's try it. And we encounter a divide by 0. That is because we are working with logarithms, and logarithms are they cannot be 0. So let's put in some safeguards to mitigate that. One, we can define some bounds. The bounds being that it cannot be greater than or less than 0 to 1. Let's do something like that. The second one is we can change our guess. Instead of zeros, we can do full and do a reasonable guess, like, I don't know, each grade you have a probability of 0.1. So let's try that. And we converge. So let's take a look at that and see what happens. See what we see. And let's call this solution. We have the solution, and we'd like to go off and plot it. So fig equals make subplots. Fig.add bar. We're doing the histogram again. Add bar x equals mp.arange n. So from 0 to 10. And y equals the solution. Pull out the solution from our dictionary. So let's try that. And you see, it looks pretty boring, right? But in reality, with our current constraints, that's exactly what we want to see. We have not defined any constraints. It's just simply, hey, what is the most probable distribution? If all I know is that there are 11 possible grades, well, then the most probable distribution is that it is equally likely to achieve every grade. So this is exactly what we would like to see. Okay, so now we can start moving on with adding some constraints. And the first one I should have added earlier, but it's pretty simple and self-explanatory. It is that the sum of the probabilities should equal 1, right? So let's call this function prob sum. Okay, and the way that SciPy handles constraints is that there's several types, and the first one being an equality. And the equality is such that it uses a root solver to make sure that the constraint equals 0. In other words, we would like to make sure that the expression, the sum of all probabilities, is minus 1 equals 0. Makes sense, right? We would like the sum of all of our probabilities to equal 1. The way we incorporate that into our root solver is that there's a argument called constraints. Okay, and it takes in a dictionary. The dictionary first would like to know what type of constraint is it, and the type is an equality. The second is that what function should it constrain, and this function is prob sum. Okay, prob sum is not defined. My goodness, what's wrong? Constraints. What is wrong here? Function is equal to prob sum, type is equal to equation. Constraints. Oh my goodness, I put it in the wrong function. What? We would like to put it right here. So actually, maybe this would rather go up a block. There we go. I don't know why I put it there. So let's try and make this look nice again. Okay. Okay, good. And shift enter. Good. So SciPy is properly accepting the constraints. So as before we saw, actually, I should have seen that the probabilities did not add up to 1, but now it does. You have a chance for 11 grades, you have about a chance of around 10, a little less than 10% to get a particular grade. And again, evenly distributed, because that's all we know. So let's begin adding more constraints. What if perhaps we know the average of the population? Okay, so let's say, what if we know the average? So define average. So pop average. Again, take some p. So then we are entirely working around the independent variable p probability to get each score. That is because these are the parameters that the root solver is trying to adjust. So we return the average would be the sum. So np dot sum of each probability multiplied by each score. So np.arange n. Okay, and let's say maybe the average is something like 6 out of 10. So let's try that. We need to add another constraint. So copy paste. Oops. Wait. I want to make sure it's formatted nicely. So maybe we shouldn't copy paste. Are we good? Are we good? No? Constraints. Oh, or maybe it needs... Do constraints need to be an array? For multiple constraints? I believe so. Yeah, that's right. Again, type is inequality. N-equality, not inequality. And the function we would like to constrain is population average. So let's try that. And would you look at that? This works out perfectly. It is going to say that the average is 6, right? So, and then it needs to adjust the rest of the scores such that the average score is going to be 6. So this is a good constraint. Okay, so now on top of the average, what if we know the standard deviation? So let's go off and add a new constraint. So let's call this standard deviation based upon the probability. So this is a little unique. You know from the past that the standard deviation looks a little something like, let's get out of here. Looks a little something like what? Looks like, oops. It looks like, well, the score a particular student got minus the mean, and you square it because you don't care about the what do you call it? You do not care about the whether it's positive or negative deviation, right? You sum that up, right? Divided by n, but then you square root everything because you don't you want to get rid of that square, right? So that is standard deviation from the perspective of the student. But we want standard deviation from the perspective of the probability to get each score. And that will look a little something like this. You would like to return the square root, right? And the sum. So just same as before. This time, on the outside, we have p. And the sum, oh, actually, it's going to be p multiplied by the difference between each score and p dot a range, and so each score minus the average, again squared, right? So should look something like that. And we already have a thing for average, so we can just define it as such. Okay, and we try that, and we would like to go off and add this constraint, right? Again, the type is inequality, and the function we would like to constrain is called standard deviation. And we try it, and square root is not defined, that because that should do np.square root. Try that again, and we get an error. And let's open this up and see what that error looks like. We have iteration limit reached. Okay, so that means it's stopping before it can really reach something. So we can try and fix this in one of two ways. Maybe first we'd like a better guess. 0.1 is pretty arbitrary. Maybe we can be a little bit intelligent about it and say, well, let's find the quote-unquote average score, completely even average score of everything. So let's do n, 1 divided by n, right? Something like that. Second thing we can do is allow the solver to go a little bit longer. And the way to do that is include an option. So options equals uses a dictionary, right? And the term I believe is maxiter. Right? And this set to 10,000, and this will allow it to run a little longer than we would originally otherwise allow. So let's try that. Also, I totally forgot that we should define a standard deviation first. So let's do something like 5.0. While I'm at it, I'm going to maybe increase the number of scores so that we could perhaps view a clear distribution. So let's increase it to 51. Okay, we have a range from 0 to 50 of possible scores, and let's say maybe the average score was 30. So let's try it out. And even though that we're getting some errors because it's hitting some walls, but at the end of the day, the optimization is terminated successfully, and success equals true. So let's take a look at what that looks like. So let's put that in a solution, right? Ignore the error and plot it out. And would you look at that? What does that look like to you? A Gaussian distribution. It just so happens that if we know the average and the standard deviation, by maximizing the entropy, in other words, the maximum number of permutations that the students can have, by maximizing the entropy, we find the most probable distribution. And the most probable distribution is a Gaussian distribution, which is why you see it so widespread everywhere in nature. You learn about it a lot in academia. That's why the Gaussian distribution is so important. So today we've shown the Gaussian distribution in two different ways. Number one is a simple numerical demonstration of the central limit theorem. I mean, look, all it took was, 5 cells? And next is maximizing the entropy equation that we derived earlier to find that, oh yeah, the most probable distribution is, in fact, a Gaussian distribution. Okay? So we'll meet you in the next video. Okay?